Welcome to Study Loop.
So in this reaction, first you have to calculate the equilibrium constant of pH3 and BCl3. In this reaction, if a sample of pH3 BCl3 is placed in a closed vessel at 80 degrees C and decomposes until equilibrium is reached. So um, to do that, first you have to set up an ice table to see the equilibrium reaction for each of the products here. So if we set up an ice table, first will be our reactant, which is a solid, and then we have our products. pH3 is a gas, and also BCl3 is gas. So now the initial concentration of this, if we assume or consider that the initial concentration is X for this solid, then for both the products it will be zero, since at the initial we don't have any product. Then the change in concentration, since it says that the sample decomposes until equilibrium is reached. So if we consider that we have um, the x molar of the concentration, x molar of the product, and that was, so if this is the concentration which is completely assumed or changed in reaching the equilibrium, then we can write down the change in the concentration will be minus x, and then change in the concentration of the each product will be plus x, since from this reaction equation we can see that 1 mole of the reactant will produce 1 mole of each of the product. That means um, the change for each of the product will be plus x if the change for the reactant is minus x. And then in the equilibrium we will ignore the reactant concentration since it's a solid, and as we know that in the equilibrium expression we don't need the solid concentration. So for that reason, we'll just write down the equilibrium concentration of each of our products, which will be x for both of them. So now from here we can set up our equilibrium constant expression. K will be equal to the concentration of pH3 times the concentration of BCl3. See, this is our product concentration. And from here we can write it as x square, since both of these concentration are x. So x square is equal to k. That means x will be equal to root over k, which is a root over this value. And if we take the root square root of this, we'll find a value of 0.0432 m. So this is the concentration of the um, so this is the equilibrium concentration for each of the reactant, so each of the products we have here. And then in the part B, we have to find out the minimum mass of pH3BCl3 that must be added to the flask to achieve equilibrium if the volume of the flask is 0.250 liter. So again, what we'll do is, from the ice table we can see that we need a change in the concentration of the reactant will be x, and here we have the value of x. That means the change in the concentration, or the minimum required concentration of the reactant, is 0.0432. So we know the concentration of the reactant which we need to reach the equilibrium, and from this value and the volume of the flask we can find the number of moles of the reactant which will be required to reach the equilibrium. So the number of moles of the reactant which is required to reach the equilibrium will be simply the product of number of moles times volume. So the number of moles which is required is 0.0432 m. m or mole per liter times the volume. So the volume here is 0.250 liter. So the product will give us a value of 0.0108 mole. So this is the number of moles of the reactant which is required to reach the equilibrium. From the number of moles, you can find the mass of the reactant. That will be just number of moles times the molar mass. So number of mole here is 0.0108 mole times the molar mass here of the reactant pH3 BCl3 is 150.5 gram per mole. So from here we can find the value of the mass, which will be 1.627 gram. So this is the minimum mass of the reactant to reach the equilibrium for the given conditions.